So here's where we are. Today we're talking about memory management and virtual memory. That's been a background topic that's sort of come up multiple times, so we're going to spend more time talking about it now and going over a little bit more about how that works and what it means. So the specific topics will be virtual memory, paging, file mapping and demand paging. Then we'll talk about how you monitor how much virtual memory is being used and how it's being used. And then finally, a few comments about how much RAM you need or how much swap space you need given how much RAM you have and so forth. So here's a typical memory map for a 32-bit system, and basically a traditional problem in Unix-type systems is to take something that looks like that and you fit it into something that looks like that if you just have 256 meg of RAM. And you need some way to do it. Where'd the slide go? There. And here, we don't really typically have that problem because our problem usually looks something more like this, where we need to take something like that and fit it into a much bigger chunk of memory. And in fact, most systems that most people have anywhere these days have at least a gig, 2 gig or so, probably, or quite possibly 4, which means you could fit an entire 32-bit image into it. So it's not as big a problem as it might traditionally be, but these are still multi-processing systems, and you have more than one process running at the same time, and each one has its own address space. So you'd still like to fit as many of those in there. So we're going to think about this really example where you're trying to fit a bigger memory map into a smaller amount of RAM and what the implications of that are. Also, let me just mention briefly that I keep using the 32-bit case for the memory map, and how that works is a little bit simpler to think about. Memory mapping is done a little bit differently for the 64-bit versions of Linux, and if you want to discuss what that looks like, then let's do that on the email list. I can give you examples and talk about that more. The other way to find out how it works, and the best way probably, is just to, on a 64-bit system, run pmap on some processes that are running and actually see how the mapping is done. Because frankly, memory mapping gets changed quite a bit, and between different versions of the kernel, I think, and virtual memory in general. And so how mapping looks on a particular system can vary over time. But the basic ideas are the same. So let's go back and look at virtual memory on a system and think about what that looks like. We talked about it before, and we have all the different parts there. And as we mentioned before, you can see the total amount of memory that you actually need down at the bottom of a pmap listing. So even though you have this big 3 gigabyte address space that you can use, in fact, you're probably not using all of it, even in the worst case. And so here for this simple little program, we're only using about 1.3 meg, and that would easily fit into a 256 meg address space. And a lot of that is shared libraries. So you would, even if you had multiple processes, you'd probably even need less than that, in fact. So it's not that big a problem most of the time. While we're looking at this slide, someone asked before about the anonymous memory allocations that are out there, and I just wanted to comment a bit more about those. We talked about the heap, and in this particular instance, I don't even, let's see, it in fact is probably already in a different spot because I don't even see the heap normally where I would expect it to, and so that actually makes the point. I've noticed that the way malloc works on current versions of Linux is that it will use the traditional heap up to a certain point, but when you get beyond that point, frankly, it will just go out there and allocate new pages of memory. And so when you look at this image, you see that there's not really a heap in between the shared libraries, the third line, and the actual executable, but there's some anonymous mappings down at the bottom. So the end result is it's kind of like the heap gets moved around, and the kernel just uses the virtual memory management system that we're going to be talking about today to create new areas of memory as they are needed. So that's what's happening there. The other thing you can see here is all the pages, all these memory segments are in units of 4 kbyte pages. So that's the page size that we'll be dealing with everywhere. So in terms of pages here, in the last one that we looked at, there were, I think, a total of 336 pages in that image. And in fact, there's over 1 million pages available in a 4 gig image. Of course, 1 gig of that is for the kernel use. So the basic idea is that we need to somehow represent the address space of a program, and the mapping of data that's in this sort of logical, theoretical address space, and how that's mapped into the actual RAM that we're going to be using. And again, I guess it would help us if the remote sites would mute your audio. So this is done through a page table, and page tables are supported directly by the CPU and the memory management unit that's built into the processor and the system on the computer. So there's a lot of hardware support for memory management on the system. And for each entry in the page table that represents a page, that's called a page table entry. And there's some flags there about the state of the page, and of course information about where it's mapped into RAM and that kind of thing. And it basically turns logical memory space addresses into real physical RAM addresses. That's the main function of a page table. And where pages go and how they're ordered and that kind of thing can vary widely. So they don't have to be necessarily contiguous. They don't have to be in order. Page tables out of the logical address space can be mapped anywhere into the actual physical address space. And also notice that you don't have to map all the pages. First of all, we've already seen that all of them aren't used anyway. We have lots of sections of memory that don't even have any data in them. There are lots of holes there. And then second, maybe some of them that aren't being used don't need to be in RAM anyway. You only need pages in RAM if you're going to be reading from them or writing to them. If you're not doing either one of those, then maybe they don't need to be there at all. And that sort of begs the question, if they're not in RAM, then where are they? And we're going to talk about that in a minute. So the kernel has to manage the actual physical memory as a resource, and it has to allocate pages out of that resource. If it runs low on available pages, then it has to figure out how to make new pages available, how to free up pages so that you can map more memory into them. And sometimes that means just zeroing out what's in the page because you don't need that data anymore. Sometimes it means taking the data that was in that page and putting it somewhere else so that you can reuse the page. So a lot of memory management has to do with that. How do you free pages? So we've already mentioned shared libraries. It's a very convenient fact that shared libraries are shared among various processes. You only need one copy of a particular SO, which is a shared object, in the actual physical RAM, and all the processes that need that shared library will be referring to those particular pages for that shared object. They might not even be mapped into the same location in the logical address space of a given process, but you should only have one copy in memory at any given time. And this is a tremendous savings over memory. The traditional way, the old way, the simple way to do this was that every process had its own complete memory image of its program with all the libraries and anything, because they were all statically compiled into the program. They were all copied out onto the loadable the executable file. Each time you ran that program, they were loaded into memory, and you had to shuffle all of that memory out of the RAM and then copy new versions in, sometimes replacing the exact same libraries whenever you did a context switch. So this is a great savings and a big optimization over memory usage for programs. So context switching, we talked about last time. That's when you switch between one running scheduled process on the CPU to another process on the CPU. And it involves largely getting all the registers values out of the CPU for that one process and then copying another set in. And it also means switching to a different address space, a different memory image. And that usually means switching to a different page table. If you have enough RAM available, you can actually have the address space for multiple processes sitting there in memory, and you don't have to do any copying of pages in and out. In other words, the process is already there, you just change to a different page table, you have a different mapping into the actual physical RAM, and a context switch becomes very fast and very easy. You just change the register values, all the pages are there, you don't have to move any in memory, you don't have to free any memory, and so it happens very quickly. That can make for a very fast system if you have enough RAM to have all the processes that you want to run on the CPU right now already in memory. If you're running short on memory, though, it's a completely different story. And then when you want to do a context switch, you probably don't have enough memory for all the pages that the new process needs, and so you're going to have to get some pages moved out or freed up, and then you can copy the other pages in. So one of the places, and again, the traditional thing that you do when you need to get pages out of memory, they're pages that you still need, so you want to save the data, and you have to copy it somewhere else to free up those pages in memory. The place that you copy it to is called swap space. So the original idea for swap space and what is traditionally called swapping was you copied all the memory, all the RAM image for a process out onto the swap space, and copied all the RAM for the new process in. That was called swapping, and that was like swapping an entire process in and out. Usually that never happens anymore. You don't swap on an entire process memory map by process memory map basis. When you do a context switch, you just move the pages around that you need to. So it's all done through paging. It's not really done through swapping anymore. So in those terms, by those definitions, you can say that a system doesn't really do swapping anymore. They only do paging now. And you only do paging, in fact, as you need to. So even though we're saying that when you do a context switch, you may need to get some other pages in, and that's true. Usually you do it on a just-in-time basis. So you bring pages into memory as you need them, as the running program tries to access them. So pages that need to be moved out of memory are copied out into swap space. Swap space is a storage area that's dedicated for this purpose. It's usually a disk partition that you allocate on a disk when you're doing the partitioning, but it can also be a file. And you can have multiple swap spaces as well. So as you add them up, the system will just use all of them. I believe you can actually specify preferences on which one gets used first and that kind of thing. To create a swap space, you use the make swap command. You can also, you use the make swap command. And then you start up using a particular swap space with swap on. So if you, for example, had the second partition on an IDE drive dedicated as a swap, then you would do that to initialize it. With most Linux distributions, they do this for you during their install process, but you can always add more swap if you need to. If you, when you're creating partitions on a disk and whatever partitioning tool you're using, the partitions have a particular type associated with them. So 83 is an ext Linux file system. If you want to make it a swap space, you usually set the type to 82, which means it's a swap type. And when the system boots up, if it sees a partition with that label on it, it will actually just add it in automatically as swap space. So you don't even have to do it. It just happens for you. If you want to see how much, what the swap space is that you're using, what devices are being used, and how much of them are being used, you can use the -S option on swap on, and it'll show you. And the units are in terms of Unix blocks. And it's worth just mentioning briefly what Unix blocks are. Most Unix commands that present their output in units of blocks, regardless of the size of blocks on the file system or the size of blocks on the actual device, they're in units of 512 bytes. So each block is half a K. So most of the time, there are exceptions to this, but most of the time, and traditionally, those commands are going to output their results in half K blocks. And I believe this is one of those cases. So that means if you see, you take the number that you have. So if you had 2,048 blocks, you divide that by 2, that would be 1,024 K, so you'd have a meg there. ls-s is an example of that. So if the fact is that we've now taken some of our memory map and we've copied it out onto the swap space, now our page table is pointing to different places for various pages. So the page table is in the middle, represented just schematically here as a set of pages, and there's information about each one of those pages in the page table. On the left is our actual physical memory, and on the right is the swap space. So if you look at that first page in the page table, that one is actually currently present in the physical memory, and it's not present anywhere else. The second page there happens to be in physical memory and on swap space. So at some point it got copied out to swap space, and then at some point later that process was running on the CPU. It needed access to that memory, so that page was copied back into memory, and now you have a copy in both places. You have one on the swap space and you have one in physical memory. There's a page, the third one down there is also present in both places, and notice that that one is red. And what I'm indicating by the red color there is that page is a dirty page. A dirty page means that one has been created, so the copy that's in memory is not the same as the one that's on swap space anymore. So the second page there is not dirty, it's a clean page, and that means that if you need that page of RAM to use for some other reason, you can just zero it and remove it from the pointer from the page table to RAM, because it's already out on swap space and you don't have to copy it out again because the copy that's out there is good. That second one's a dirty page, and if you need that page of RAM, you're going to have to recopy it out to swap space again. So when the kernel is going through trying to free up pages of RAM, that's the thing that comes into play. Whether pages are dirty or not, dirty pages have to be copied back out to swap space. Clean pages don't have to be. The fourth page down there near the bottom is just mapped into physical RAM. It's never been copied out to swap space. So this is a case again where if you needed to free up that memory, then you'd have to copy that page out to swap space. And all of that tracking is kept up with in the page table itself. So when does this happen? When do pages get copied in from swap and so forth? It happens when the program is running along and is tracking through the memory address space. And you can think of the page table in the middle as sort of being a direct map of that address space that we were talking about. So as you're going through there running instructions, you might hit an instruction in a page of memory that's not present in physical RAM. And what that does is cause, at the hardware level, a page fault, which basically says, I've just accessed a chunk of memory that's not in RAM. And so that causes the kernel to go into its page handling code and go out and find that page and then get it copied in. So that's when copying from swap would have, or copying from somewhere. And in fact, if you're ready to copy it into memory and you find out you don't have enough pages there, then you have to go through and start working to free some pages too. So that's what causes that to happen, or at least one thing that causes it to happen whenever you're trying to access the memory. The other important point about that is that causes the page in to happen when you need it. So it doesn't happen ahead of time, it just happens on demand. The downside of that is if you're having to page something in out of swap space, there's a really, in relative terms, long wait for that to happen. It takes a long time to get pages in from swap space. So if that happens a lot, if your program's running along and it keeps hitting page faults and you have to wait for pages to be paged in, your program is going to run very, very slowly, because the relative speed of getting stuff in from disk is a lot slower than getting it from RAM. So basically what this boils down to is if you have a lot of paging going on a system like this and it's causing it to be slow, then you need one of two things. You need to be running less program on the system so that there's just less demand for paging, or you need to have more memory so that you can have more of these pages just remaining in memory and not getting paged out to swap space. Interestingly enough, I believe that it's the case here that on a lot of systems we don't even use swap. There's not even any swap space allocated. So the expectation is that everything that you need fits in memory, and there's not even swap space to swap it out on. It is the fact that swapping in and paging in is worse than paging out. Paging out can be done later at some point, but it's when you have to wait for the page to be copied in that's the problem. So that's one example of what's going on. with paging out to swap space, but there's another optimization that's come along in recent years. And again, let's think about the virtual memory space that we have. We run the process, we have the text of the program, we have the initialized data, the uninitialized data. We need to get all of that into the virtual memory space. Later on, we need to reuse some of those pages of memory, and so we copy that stuff out to the swap space. Now the point is, some of this is read-only. It's never going to be changed. For example, the text of the program. And the old way to do this was you had copied the text of the program into pages in memory, and now you need those pages, so now you're going to copy it back out to the swap space. Now you have the actual program two places on disk. You have it in the original bin file, where the original file was, and you have it out on the swap space. And the question is, why not just go ahead and let the program itself on disk be its own swap space? Why do you need to copy it out to the actual swap device? You can just use the one that's already out there. And so that's what happens in this case of file mapping, is you just use the original copy of the program as its own disk copy of what's in memory. And if you need to free those pages, you just free them up, and if you need that program, those program pages in memory again, you just copy them back from the original file. And as long as you're going to be doing that, then why even copy them all in the first place? Why don't you just go ahead and map that file into memory and say, okay, these memory pages correspond to these memories on disk out in bin, whatever the name of the program is, or user local bin or whatever. And when you get to that page of memory, when you're running the program, you get a page fault and you just copy it in when you need it. This turns out to be a big, big win. Because the fact of the matter is that when you're running most programs, you don't use all of the text of the program. You don't run through every single function that's there. You don't go through every part of some conditional loop, conditional or whatever. And so there's a lot of chunks of program that don't get run. And I think an example that I've heard mentioned before is the ls command. Right? The ls command has just tons and tons of options. Even if you look all the way back to Unix version 7, the ls has a whole page full of options that are available. Usually you don't use most of those. You use -L or -T or -D or something like that. So there's a lot of code there that never gets used. So there's no reason to copy all of that code into memory. So this is really a big, big win, because when you load a program, then you just map the file, and here we've represented the program as the blue pages out on disk. That's the actual file. And all of those are immediately mapped into the address space, but in fact you just bring them in as you hit those pages. And as shown in this example, we're only using the middle page out of the program. That's probably not a real world example, but it's close enough. And that's a big win for loading the program. That's called demand paging, because you only load the pages as they're needed. The same thing happens for shared libraries, and we already talked about that basically. The shared libraries out on disk, you just map that image into memory. Nothing ever goes out to swap space for that particular program. The other thing you can see from this picture is now we're using less swap space. The only thing that we use swap space for are pages that are in memory that are not associated with some real-world file. So that means it's only data, either data for the program or data that's dynamically allocated later. So that's why it's called anonymous. Those pages are called anonymous pages, or those memory segments are called anonymous, because they're not represented by some other real-world file that's out on the disk. And that's what goes to swap space. Well, if it's just anonymous memory that goes to swap space, you need a whole lot less swap space than you might have on a traditional dumb system that doesn't use file mapping and demand paging. So the demand on swap space is much, much lower in this case. So I don't remember if we talked about it before, but the actual code that does the loading of shared objects is the ld.so, and if you look at every program, you'll see ld.so. That's the shared object loader. That one's always loaded in there, and then its job is to go out and find the shared object when you load the program and map that in as well. I also didn't mention copy on write. So we talked about when you fork a process and the whole copy on write process. Copy on write actually turns out to be a flag that's set on a particular page in the page table entry. So when we load, for example, if this program that we're looking at right now that's running wants to do a fork, then the pages that are there would be set to copy on write, and if any of them were changed, then there would be a new page table entry created or there would be a new page that would be allocated by the kernel for that particular page in the page table of the new process. Otherwise, it would just be pointing. It would be pointing to the existing pages for the old process, and would actually be using the page table entries as well. And so that's how that's implemented. It's actually done through the page table, and there's a flag for every page that indicates whether it's copy on write or not. So this whole idea of demand paging, of really getting a page fault and then having to bring that page in as the program is running, you might say, well, didn't we just say a few minutes ago that paging is bad, that having to stop while your program is running, have a page fault, and then wait to load that page into memory, isn't that going to slow your program way down? And the answer would be yes, but the fact of the matter is that if you hadn't done that, the alternative is to load all those pages into memory in the first place. So you would have this really long delay while you copied every single page of the program into physical memory, and here you're not having to do that. Here you get that time back for free because you immediately start running. So you fault on the first page, copy that one in. You only have to wait for copying one page instead of all of them. And yes, you have to stop and then wait for other pages to come in, but it's still a win. You're still copying less pages in than you would if you had to wait for all of them to be paged in. So overall, in most cases, the demand paging would be a win over the alternative, which would be copying them all into memory. And again, that's partly because a lot of them are never loaded into memory in the first place. So with all of this information about paging and swapping and so forth, the next thing you want to know is how much paging is going on my system, how much swap space am I using, and you want to be able to monitor how that's going. So the vmstat command is an excellent way to do this. If you run vmstat, a space, and then 1 for every second, and then a space, and you can say how many times you want it to actually run, that will give you nice feedback on what's happening on the system as far as memory management. Always remember with vmstat that the first line that prints out is actually an average over time. So that's not a sort of just an average over the interval of 1 second or whatever, but it's an average over the whole history. So ignore the first line, or at least interpret it that way, and then watch what happens for lines after that. So some of the columns that are interesting there are the swapped column, which shows you how much memory, and I think this is in units of kbytes in this case, how much is actually in the swap space. For the RAM, it shows you how much is free, and then it shows you how many page ins, and it calls them actually swap ins and swap outs, but it means paging. How many page ins and page outs are happening. There's also another couple of columns here that are BI and BO. Those are block reads, block read ins, and block read outs. And typically, if there's just paging going on, they'll be exactly the same. The block I/O that's happening is actually the paging I/O. Linux does a pretty decent job of distinguishing between those two. So if you have any block I/O that's happening that's not paging, then you'll see the difference there. So if you see your free memory going down, and it'll only go down to a certain minimum limit, and when it hits that minimum limit, then the kernel is going to have to busily start going through and trying to free memory. And so that actually happens. And you can see the size of free memory go up and down as you run more and more programs and start creating a larger demand on memory. And watching that in vmstat is a very useful way to do it. The other thing that's going on, though, is that in fact, for example, with ext2 and the ext3 file system, that file I/O itself is done through the paging system. And this is not just a Linux thing. This is true other places, like Solaris is one that comes to mind. So when you need to do I/O on a file, you just map that file into memory, and then you let the paging system take care of reading and writing from the file as well. So a lot of times you'll see paging. That doesn't mean that you're actually paging because you're running into a memory problem. It's just normal I/O on files that's going on. So that's something else that you'll see as well. And with systems, it's it's not always the case that if you see a high level of paging that there's a problem there. So you have to watch for that. It's better to look at how much swap space that you're using or not, because if you're doing file I/O, you're not using the actual swap space. It means that you're mapping some other arbitrary file out on the disk into memory. And by the way, that's just exactly like mapping the initial program. You can map other files into memory as well the exact same way, and then read and write from those files just by accessing the memory. In the case of Solaris, Solaris has a particular page scanner that in the kernel that goes through and tries to free up pages. And in the Solaris version of VMstat, it actually shows the scan rate. So that was one way in that operating system to tell whether you had a paging problem or not. If the page scanner was actually running and you see the scan rate not 0, but it's really desperately scanning through pages to try to free them up, the size of that number would tell you how much of a memory problem you had, not how much actual paging was happening. So another way to look at what's happening with virtual memory is to look at these two files in the proc file system. One is under the actual directory that represents a particular process, and the name of that directory is the process PID, and it's called smaps. And that shows you a very detailed summary of every page and the state of that page. We'll look at some examples here. The other is the meminfo, which gives you lots of information about the overall system memory and how much of it is being used for various purposes. So when you look at the smaps output, for every page it shows you the name of that page, if it's associated with some file. For example, the program that I was using here was called a.out, the default name when you compile a program. And you can see there that there's the size of that page, which is 4K. That actually, I'm calling these pages, these are actually memory segments that can be made up of multiple pages. So the size of this segment is 4K. The RSS is the resident set size. That's how much of this segment is actually present in physical memory, how much of it that is mapped right into RAM now and is currently present. So that's RSS. You'll see that term a lot, and that always tells you how much of your virtual memory is in real memory. So all of it, in this case, the entire segment is in real memory. It's one page anyway, so it pretty much has to be. And then it shows how much of it is shared, how much of it is not shared, and whether it's clean or dirty. So here we see that because this is the read-only program, it has to be clean. You can't write to it, so it can never be dirty anyway. And then you actually see the range of addresses, the permissions on them, and I forget what the other number, I forget what that number is, and not sure about the time either. I'd have to look at that. That may be how long it's been present. In this case, we're now looking at some of the data for the program. Oh, you know what? I remember. There's an error on these slides, and I had completely forgotten about it. That line at the bottom is the line for the next memory segment. So this one is actually, the line there, because it's read-write, corresponds to the one below it, and I think that's this one. So basically ignore the bottom line in this case. But this is actually the data for this program. And you see again the data segment's just a 4K page. And this time it's dirty. It is resident, but it's dirty. And so if you were going to free up pages in memory for this, you'd have to swap it out to swap space. Here's an example of a shared object. In this case, it's actually 84K. It's pages in size, but not all of them are resident. Actually, only 80K of those are resident, so there's one that's still just part of the file that's out on disk. It's never been paged in, and it's all clean. So then we can look at some of the memory info that you can get out of the proc file system as well. And here you can see the total amount of memory that you have. Everything's units of kbytes. You can see how much of it is free, how much of it is actively being used, and how much of it's inactive. The total amount of swap and the total amount of swap that's free. And on this particular system, all of it is free. None of it's being used. We see how much of the pages are dirty. And then we see how much memory we're actually using for page tables to keep up with page table data. So there are lots of... There's been a lot of work on how you go through and manage memory and how you free it up and that kind of thing. And when you're running low on memory, generally the kernel just has to do something to go out and find new memory. And one of the old ideas was the so-called clock hand algorithm, where you would have code in the kernel that would go down through and it would mark pages that hadn't been accessed. And then whenever they were accessed, that flag would be cleared. So then you would come along behind with another chunk of the program, and it was like, you could think of it as two hands of a clock going around a face, so one's going around marking, then one's going and checking. And you would come along and check if the flag had been cleared, meaning that page had been accessed. If it hadn't been accessed and hadn't been used, then that was a page that you could free. And again, if it was a dirty page, you would free it by either swapping it out or adding it to a list of pages to be swapped out, or if it wasn't dirty, you would just zero out the page and make it an available page again. So that was one algorithm. There are fancier algorithms now, but a lot of times they revolve around this idea of if you want to get rid of the least recently used pages, the pages that haven't been accessed in a while. If they're not being used, then they're pages that you can free up in memory and use for something else. There is a kernel thread called kswapd, and it actually goes out there and will try to free up pages. If the system these days runs dangerously low on memory, and the system is trying to free pages and it can't because as it swaps between all the processes that are trying to run, there just aren't enough. There's not enough swap space to swap pages out to, and there's just nothing to do. Then something kicks in called the killer, which is the out-of-memory killer. And I actually experienced this before I realized it was there. I'd never heard of the killer before. But it's code in the kernel, and it's really quite clever. It uses an algorithm to go through and try to pick a process that it's going to kill because it can't free up memory any other way. And it'll actually just start killing processes for you, trying to save the system at the expense of at least some program that's out there running. If you're so low on memory that it's not that you've run out, but that you're just constantly having to copy pages out to swap space and page them back in, that's called thrashing. And I don't see people experience this as much on Linux systems, but I see people experience it a lot on Windows system, which basically work the same way. And when people have not enough memory on their Windows system, it gets really, really slow. And you can look at the task manager and see that it's trying to commit and use a lot more memory than you have physically, and so it's just constantly paging. And that makes a system feel like it's basically practically stopped and not even running anymore. And again, that just means that you need to add memory or reduce processes, one of the two. So the way that swapping used to work is at the time when you were going to have to take every single page, and when you needed that page in physical RAM to free it, you had to copy it out to swap space, and there was no file mapping and demand paging and that kind of thing going on. Then it made sense to say for every page of RAM you need at least one page of swap space, and in fact you might need more. So you'll see this rule of thumb a lot, that swap space should equal RAM. But with the modern view, where you really only need swap space for anonymous memory, you don't need it for programs and other things that are going on. Also, you don't have to, at that time when you allocated a page in the logical memory address of the process, it would automatically allocate a swap space page for that memory. That doesn't happen now. You can have a page in memory or in swap space, but sometimes not necessarily in both. So in fact, you can add together the RAM that you have and the swap space, and that represents the total amount of virtual memory you can have, because pages don't have to be in both places at the same time every time. They can be in one or the other. So that's the best way to think of it now, is in fact that the amount of memory that you need is not swap plus some extra, or not at least equal to swap, but in fact you can think of it as the amount of physical RAM that you have plus the amount of swap space. So here's an example. Let's say that you think that you need 8 gig for a system to run, a database server or something. You have 4 meg of RAM, then you might want to have 4 meg of swap in order to have that 8 gig available as virtual memory. If you then increase the amount of memory in the system to a total of 8 gig of RAM, then you don't need another 8 gig of swap. It's not that you need a total of 16 gig of virtual memory now. In fact, maybe you need no virtual memory at all anymore, or rather no swap space at all, because you can just do everything in RAM. So it doesn't make sense that you always need the same amount of swap space as you need for RAM. Okay, so I think we're done. Once again, a little bit ahead of time. So I'll take any questions that you have.
So you said whenever a program first starts, page faults and then swaps or allocates a page.
Right.
For new files that it wants to allocate pages to, will it just uses the same method? Fail once, then write?
Yeah, you mean for just reading in a file? Not for loading the program, but you just want to read in some arbitrary file?
Or write to a file?
Or write to a file, yeah. You want to open a file for I/O. Then, yeah, that's done on I believe, and we'll talk about this more when we talk about ext3, but yeah, the file I/O is done the same way you map the file, and I think it might vary depending on whether you're reading or writing from the file, at least in some versions of Linux. So I'll need to go back and try to be precise, but that's the basic idea. You map the file into memory, and now if you're writing to the file, it's a little bit different because there's nothing out there to map yet. And so writing goes through maybe a slightly different process, but certainly for reading in a file that already exists. So did that make sense, or was that... Yeah, that does. Reading a file is exactly like loading a file to run it. With writing a file, you actually have another whole job to do, which has to do with the file system and going out and finding blocks that are available and allocating those and creating an inode and all that kind of stuff. So we'll talk about that.
How about you were talking about the executables in like the bin directory, and you'd execute them, and it used to be that they would load the entire executable into memory, but now it only pages in when things are needed.
Right.
I was a bit confused on. It sounded like you were saying that these executables are already living in memory, but I'm guessing that they're executed, right?
So there's really two cases, and that's a good question. If I'm running a program for the first time, then there's nothing in memory. But at the time that we do the exec-ve system call and start running the program, it still doesn't. We still don't copy any pages into memory at that point. All we do is we allocate where those pages are going to be in the page table, in the page table in the middle there. And we say, okay, this page corresponds to the first page of text, and this page corresponds to the second page of text. And now those pages that are in the file are mapped to somewhere in memory. And then the instruction pointer is set down to the first address where it's going to start running. And now it starts trying to execute instructions. And what it does is it tries to access those instructions in memory. And when it hits an instruction on a page that's not physically copied into memory, that'll cause a page fault to happen. And now we'll go through the page fault code, and we'll actually go out, the kernel will find that page on the disk and copy that into RAM, and then it'll go on its merry way executing instructions out of that page until it hits another page that's not in memory yet, and then a page fault happens again, the kernel will go out, bring that page in, and so on, and hopefully before long you have all the pages that you need in memory, and you can just keep executing the code out of those pages. Now, let's say that your program actually gets to the end and finishes, and it exits, and the memory map for that program has gone away. The kernel still keeps those page table entries around, and those pages are still in memory. And if you don't need that memory yet, then why not just leave them there? So the next person comes along to load this program, and at the point of the kernel going out and mapping the program into memory, it can actually look and see that there are already pages of that program in memory, and so it just maps directly to those pages, and also there's still those page table entries are already mapped out to that actual file, and so it uses the ones that are already there, and now we don't have to page anything in. It's just sitting there. So you'll actually see this happen when you use a system and you run the same programs over and over, and if you have a lot of memory, eventually you'll get all the data that you need, all the code in RAM, and there's no disk I/O happening at all. And this actually becomes really important on servers. If you're running a web server and you're using the same code all the time, and you have enough memory, then there's no disk I/O going on as far as loading programs, even if you execute a new program. Everything gets paged into memory and it just stays there. So issues with disk I/O as far as loading programs and executing them, you can sort of make those go away with enough memory. So does that help?
Yeah, that was great. You actually answered the second question too about, you know, if I were to run program again, I imagine a lot of the shared libraries probably stay in memory at that point. So that was sort of my second question, and you answered that. So thank you.
Yeah. Same thing with shared libraries, even if you're not running the same program. So the whole trick here is how often do they get used. If they're getting used a lot, then that'll cause the memory freeing algorithms to just leave them there, so that they get reused, and there are big wins that come out of that. If they're not getting used often enough, or if there's just a lot of pressure on memory and there's a lot of freeing that has to go on, then the unfortunate thing that happens that you really wish didn't happen is that then you start taking pages out of memory that you really want to stay there, and that's when a system starts slowing down a little bit, or a lot, depending on how bad it is.
I was just going to ask, is there any word that you would recommend that we read to get like just an overview or a little bit more information that would maybe enhance the slides a little bit?
Definitely, yeah. The references that are in the first part of the class, and particularly the O'Reilly book on understanding the Linux kernel, that's absolutely the best source of information. And it does a lot of work on explaining virtual memory. In fact, it spans several chapters in that book. So it takes it one step at a time and covers it in a lot of detail, but it covers it at a very readable level. So by far, that's the best source of information. If you're looking for something quicker, then there's some. There may be some other. I don't know if you can look. I think you can look through the archive for the class mailing list, and some folks sent out some nice links last time. So you might look through those, and if anyone knows of any links that you like in particular, you might want to share those with us as well. But by far, that kernel book is the best source that I know of for finding out about this, because it's readable, but it goes into enough detail that you can understand everything, I think, as much as you would like to.
Another book that I've actually started reading is Advanced Programming for the Unix Environment. That seems to be pretty good too.
Is that the Richard Stevens book?
Yeah.
Yeah, that's an excellent book. I actually took a class from him on that topic, and he was a fantastic teacher in the classroom. So his book, which I've never actually read all the way through, but just parts of, is equally excellent. Yeah.
Can you discuss some of the strategies that we use here in our production servers with virtual memory? I know that on our index machines we have a single disk. We don't have a swap partition.
Right. As far as I know, we don't have swap partitions on any production machines anywhere. So basically things are designed so that you don't have any swapping going on. You can check and see if that's true, but that's what I understand to be the case. And that's the best world, right? To not have any, just not do it. And in fact, you take a desktop system these days. If you buy one with a few gig of memory, if you look at it, you'll probably never see any swapping happen. You have to work at it to actually make swapping start happening.
The killer?
Yes.
Does that go and go after user processes first, I assume? Like large memory using user processes?
I think, and I'm not really sure, I'll have to go back and look at this, but yeah, it sort of, I think what it tries to do makes sense in most cases. It goes after processes that it thinks are not critical to the system, and then after that it may look at, the ones that are causing the most trouble, but I don't know exactly how it determines that. I'll actually look at that and get back with you on the mailing list to make sure I get that right. But it tries to be sort of intelligent about what it does. And that's what I would expect to happen on a system. You can certainly try this out. I think, and I've tried it before, if you go out and write some program that is intentionally written to use up all the memory to test it, I think it will definitely go after your program. So the question there is, how can I write a program that the killer is going to ignore and go out and kill something like SSHD or cronD or something? That would be an interesting exercise, I guess, to try to defeat it. All right, well, I will look forward to seeing you next Monday, and we'll go from there. Thank you very much.